Hello everyone, and welcome to my talk on certifying decision trees against evasion attacks by program analysis. I'm Stefano Calzavara, and I present a joint work with Pietro Ferrara and Claudio Lucchese. We're all affiliated to Università Ca' Foscari Venezia, Italy. In this talk, I will tell you something about the security of machine learning. Machine learning is a sort of hot topic in computer science nowadays, as you certainly know, because it is becoming more and more popular and found tons of new applications. You can find some examples here, like automatic language translation, medical diagnosis, stock market trading, and so on and so forth. And what is striking is that machine learning now is even better than humans on specific tasks, which can be solved by machine learning more effectively and efficiently than human beings. A key area where machine learning is getting a lot of popularity is related to classification tasks, where we feed an item to a machine learning model and we get a prediction about its class. For instance, if you think about spam filtering, a spam filter just picks an email as an input and will tell us whether this email is spam or ham. Unfortunately, even something as cool as machine learning has a dark side, because previous research showed that even when performing machine learning model might be fooled in practice. For instance, let's consider a spam message. Congratulations, you have won a free $1,000 gift card. What the attacker can do, after noticing that this message is flagged as spam, might be changing the content of the message slightly, and for instance replace congratulations with congrats, which is shorter, and then remove the free keyword from the message, and what the attacker would get is a message which is semantically equivalent to the original one for a human being, but still this message might be turned out to be classified as ham by a spam filter. When we deploy machine learning model in a security-aware settings, we should be aware of the possibility of evasion attacks like this, where the attacker manipulates an input such that a wrong prediction is forced by the classifier. In this talk, we focus specifically on the security of classifiers, where a classifier is just a function h which assigns to each element of vector space X, also called instance, a prediction from a finite set of class labels Y. For instance, a spam filter is a classifier which, given an appropriate representation of a message, will give me one between spam or ham as binary label. So it's a binary classifier. When evaluating the performance of classifiers, we typically rely on a loss function with the idea that good classifiers are characterized by a small value of the loss. To estimate the value of the loss, we rely on a dataset of elements which are labeled with the correct class information. For example, we might define the loss by counting the number of mispredictions which we perform on a set of correctly labeled data. This is exactly what you see in this slide, where we first define a notion of instance level loss, small l, which, given a classifier h, an instance x, and a correct class label y, returns 1 if the prediction of the classifier is wrong, and 0 otherwise. By summing the value of the instance level losses, we are effectively counting the number of mispredictions which are performed by the classifier over our dataset D. The key problem with this definition is that it is not representative of what might happen when the classifier undergoes attack. To overcome this limitation of the definition, we can rely on a new notion, which is the notion of loss under attack, which is particularly useful when classifiers are deployed in security-sensitive settings. The key idea is that we can represent the attack as a function such that, given an instance, will give me a set of possible perturbations of the instance. And once we compute the value of the loss, we are not focused just on the original instances which are in the dataset D, but we also take into account the possible adversarial manipulations. The key idea is that rather than aggregating the individual instance level losses, we take all the possible attacks into account by picking for each instance the maximum value of the loss which might be forced by an attacker which tries to perturb instances before the classifier performs a prediction. In other words, if there is even a single attack which forces a misprediction by the machine learning model H classifier, we consider a misprediction because we assume conservatively that the attacker will be able to craft such a dangerous attack. The key problem of this formulation is that it is very nice formally, it's very intuitive, but computing the value of the loss under attack might be complicated. In particular, previous research proposed different techniques to deal with this problem. The ideal solution, of course, would be an exact computation, where we compute the right value of LA, but doing something like this presents scalability issues. The reason why this computation is hard to do is that we are computing a maximum over all the possible adversarial manipulations. If the amount of adversarial manipulation is large, computing the maximum in the set might be something which does not scale. So, we might resort to approximations of the loss under attack. We might, for instance, use some under-approximated analysis, so we try to craft an attack which will evade the classifier with high probability. But since we are not enumerating all the possible attacks, this technique is under-approximated, which means that it might suffer from soundness issues. We get a picture of the performance of the classifier under attack, which is somewhat optimistic, because we are missing attacks. So the other side of the spectrum comes from over-approximated techniques, where we don't compute the value of LA, but we compute an over-approximation of such value. This will be sound, and it's a nice property, but so far this has only been done for artificial attackers. For instance, cases where the attacker is represented as a mathematical distance, and we have simple ways to approximate its behavior. What we propose in our paper essentially is the first security certification technique for a class of machine learning model, which is the class of decision trees. And this technique is sound and scalable while supporting a very expressive threat model, because we assume that the attacker can be represented as an arbitrary imperative program. In our paper, you will find the design of a general certification technique for decision trees, an implementation of this technique in terms of a tool, TreeCert, and the results of our experimental evaluation performed on free public datasets. Before we start digging a little bit more into the technical details and the result, let me tell you a little bit more about decision trees. Decision trees are very simple classification models where binary tree, whose internal nodes perform some checks over instances, and the leaves tell me which class the instance should belong to. You can see an example decision trees here in the left part of the figure. What we do here is that we first check whether the second feature of the instance is less or equal than 10. If this is the case, we go in the left subtree. If it is not the case, we go in the right subtree. Note that the right subtree is a leaf which assigns the class +1 to the instance. Instead, the left subtree is an internal node which contains another check where we verify whether the first feature has a value which is less or equal than 5, and if the test succeeds, we go in the left subchild and we give +1 class to the instance. Otherwise, we go in the right child and we give the class -1. For instance, if we want to assign the label to the instance 87, what we do is that we notice that the instance satisfies the first check we go in the left side, then the second check fails because we have 8 which is bigger than 5, and we go in the right leaf and we assign negative class to that instance. The first observation we make is that any decision tree can be easily converted into an imperative program. For instance, the tree on the left can be represented by a simple predict function, which given an instance x performs some conditional checks, possibly nested, and returns me the class, which is the prediction performed by the decision tree model. So in a sense, decision trees are interpretable, so they're very easy to understand, and can be represented as imperative programs. The key idea of our approach is that just like the decision tree can be seen as an imperative program, we can also model the attacker as an imperative program. And more specifically, we represent the attacker as an arbitrary function which has a non-deterministic behaviors and operates before prediction time. So the key idea is that to model the behavior of a classifier under attack, we replace the predict function in the previous slide with a new function which is called predict under attack. And the key idea of predict under attack is that given an instance x, the first thing we do is that we call an attack function which will give us a non-deterministically chosen possible perturbation from all the possible set of perturbation by the attacker, call it z, and we return the prediction which is performed by the classifier over z. What is nice of this model is that it is very intuitive, and since the attack function can be an arbitrary imperative program, we can model different cases which are supported in the literature. For instance, we can simulate cases where the attacker is just a mathematical distance, and we can do that by doing sampling within a given distance from the original input. Or we can support more expressive cases where the attacker is modeled by means of rewriting rules, which are applied to the original instance up to budget exhaustion. For instance, I show you in this slide how we can represent the cases of rewriting rules. In this threat model, which has been proposed in a recent paper, the idea is that the attacker can manipulate instances by having access to n possible rewriting rules. Each rule has a cost and a set of preconditions. And the idea is that if a precondition can be satisfied and the attacker still has enough budget, the rule can be applied to perturb the value of a given feature, for instance by adding a delta to the original value. And these rules can be applied up to exhaustion of the attacker's budget k. As you can see in the left part of the slide, we can model the behavior of the attacker by defining the attack function appropriately. The idea is quite simple. We start from a float variable k, which has value 10, and until we are not done, we randomly pick one of the writing rules available to the attacker, and depending on the rule, we just apply the perturbation which is encoded by the rule, and we pay the price of the rule. For instance, if we have a rule which requires the first feature to be less than or equal to 0 and has cost 5, we do this conditional check, we sample a random perturbation, for instance let's say between 0 and 1, we modify the feature by adding the perturbation delta, and we remove the cost of the rule from the available budget. And we do this up to budget exhaustion. The key idea is that this attack function has a non-deterministic behavior because it relies on random sampling, but each branch of the non-determinism will deal with one possible move by the attacker. Once we represent our decision tree under attack by an imperative program, the cool point is that we can use standard program analysis techniques like the abstract interpretation framework to over-approximate the output of the classifier which is undergoing attack. The key point of our reasoning is that since abstract interpretation is a sound analysis tool, it must be able to cover all the paths of the non-deterministic program execution. That means that all the possible adversarial manipulation must be correctly taken into account by the abstract interpretation framework. In the end, since the program that we model is non-deterministic, because the attacker can perform multiple different actions, the output of the analysis is a set of class predictions which can be made by the classifier under attack. If the set of the class prediction contains only the correct class label, we are sure that there is no attack, because the set of class prediction is an over-approximation of the whole program behavior. Otherwise, we know that an attack might be there, but we might have a false positive. We implement this analysis inside a tool which is called TreeCert, which is built on top of the Apron analyzer for Java. The key idea of TreeCert is that we start from an attacker model and we consider the rewriting rule-based attacker which I mentioned. We then have a decision tree. We call a first component, which is a tree coder, which returns us an encoded attacker representation and encoded tree representation as Java programs. We then analyze the attacker to come up with invariants which model the attacker behavior, and we feed the attacker invariants as well as the encoded tree to a new model called tree analyzer, which will tell us whether each instance which is fed to the decision trees is classified correctly or not. The output of our analysis is eventually an over-approximation of the loss under attack, and this over-approximation is sound because the abstract interpretation framework is a sound program analysis engine. To evaluate the effectiveness of our proposal, we compare the result of TreeCert against the result we would get by the representative attacks approach presented in previous work, which provides an exact computation of the loss under attack for decision trees. We try to answer three different questions. Can TreeCert compute a tight over-approximation of the loss under attack? Can this over-approximation be efficiently computing? And what is the impact of the attacker budget in our analysis? You can see in this slide results over three datasets, census, house, and wine, where for different values of the attacker's budget, we compute the value of the loss with no attack, which is the first column here, the value of the loss under attack, which is the second column here, and then you can see the approximation which is computed by TreeCert. As you can see, empirically, the approximation is very tight. It is indeed an over-approximation because the third column is always larger than the second column, but it's actually very, very close. And what is cool, you will see in the next slide, is that the performance of TreeCert is really impressive, because the solution based on the representative attack computation proposed in prior work does not scale, and in particular has an exponential blow-up, which means that the solution becomes easily unusable when the attacker's budget grows, while the time spent for TreeCert to perform the analysis is almost constant and does not change significantly with increased budgets from the attacker. To conclude, machine learning models are susceptible to evasion attacks. Designing sound certification techniques is very important to prove the security of such model and convince about their effectiveness in security-aware settings. Program analysis is a sound, scalable, and expressive technique nowadays, and in this paper we argue that it can be fruitfully applied to this task. We are still working in our project, and we are extending the proposed approach to other cases like decision tree ensembles, like random forest and random boosted decision trees, and regression tasks where rather than predicting a class, we predict the value of a continuous variable. And we hope to come up with good results soon. And thanks for your attention. If you're curious, please see the bibliographic references in this slide.